In this video, we're going to discuss term-by-term differentiation of power series. Suppose we have a function f of x, and we know a power series representation for that function, say series from n equals 0 to infinity of c sub n x to the n, which we can write out with the first few terms c0 plus z1x plus c2x squared plus c3x cubed, and so forth. We can then ask whether it's possible to use this power series representation for f of x to find a power series that represents the derivative of our function, f prime of x. Intuitively, we could proceed as follows. We know that f of x is equal to this power series, which is essentially an infinite polynomial. And we know that polynomials are easily differentiated. We can just look at each of the terms here in our polynomial and differentiate each of them using the power rule. And so if we did that here, we could differentiate each of these terms term by term. And so the derivative of c0 would be 0, since c0 is just a constant. The derivative of c1x would just be c1, since this is a constant times x. The derivative of c2x squared would be 2 times c2 times x. And the last term we have written here, the derivative of c3x cubed would be 3c3x squared. Of course, we could continue this on indefinitely and differentiate as many terms of this power series as we'd want. Now notice that we could, in fact, differentiate the general term of our power series. So we would have n equals 0 to infinity of a constant cn times x to the n. And when we differentiate this with the power rule, we're going to get n times c to the c sub n times x to the n minus 1. The logic used here is very intuitive, but we are extending what we understand and know about polynomials to a power series, and certainly there is a question about whether that can be done. In particular, if f of x is a finite polynomial, we know that everything that we did here was absolutely correct because we know how to differentiate a polynomial. So the question here is whether that same reasoning can be applied to an infinite polynomial, which is a power series. And fortunately, the answer is yes. We can formalize the answer to this question in what is typically called the term-by-term differentiation theorem, which states the following. Suppose that we have a function f of x, which has a power series representation centered at a of the form n equals 0 to infinity c sub n times x minus a to the n. Also assume that this power series representation converges on the interval from a minus r to a plus r. This is just another way of saying that the radius of convergence for this power series is r. If we have such a function in a power series representation, then f prime of x, the derivative for f, can also be represented as a power series on that exact same interval, and therefore will have the same radius of convergence r. And the power series representation for f prime of x will be given by the sum from n equals 0 to infinity of n times c sub n times x minus a to the n minus 1. Notice the term of this power series representation for f prime of x is obtained by taking the term for the power series representation of f and differentiating. And so here we take c sub n times x minus a to the n. We differentiate that to obtain n times c sub n times x minus a to the n minus 1. The same thing then happens with all of our other terms if we look at the terms individually. The derivative of c0 is 0, which is not listed in our representation below. The derivative of c1 times x minus a is c1. The derivative of c2 x minus a squared will be 2c2 x minus a. And the derivative of c3 x minus a cubed will be 3c3 x minus a squared. And of course, we could continue on with as many terms as we want in our power series representations. The punchline here is that if we have a power series for a particular function and we want the power series for the derivative of that function, it is quite easy to do. We simply differentiate the power series term by term. For an example, Let's find a power series representation for the function f of x equals 1 over 1 minus x quantity squared. Once we have this power series representation, let's use this to find the exact value of the series from n equals 0 to infinity of n over 4 to the n minus 1. First, for the power series representation of our function, notice that there's really no way to manipulate this function 1 over 1 minus x quantity squared into being a geometric series. We could try various substitutions and things like that, but there's just no way to algebraically manipulate this into that geometric series form. Once we know that algebraic manipulation is not going to help us here, we might try to write this function as the derivative of a function whose power series we know. We really at this only know one basic power series representation, which is 1 over 1 minus x. So we might start by determining what the derivative of 1 over 1 minus x is. Of course, there's a couple different ways we could compute this derivative. One way is to rewrite our function as 1 minus x to the negative 1 power and use the chain rule. So here, if we use the chain rule, we first differentiate the power function. So we'll have a negative 1 times 1 minus x to the negative second power. And then the derivative of 1 minus x is negative 1, so we multiply by that. And of course, our negative 1s will cancel out here. And we're left with 1 minus x to the negative second power, which we can rewrite as 1 over 1 minus x quantity squared. Now, of course, we observe that this function is exactly the function that we're looking at in this example. And so what we're being asked to find here is the power series representation for the derivative of the standard geometric series function. And so we can use term-by-term differentiation to find this power series representation. We start with our power series representation for 1 over 1 minus x, which we know is the sum from n equals 0 to infinity of x to the n. And we can even write out some of the terms here. We know we'll have 1 plus x squared plus x cubed, and so forth. So the first 4 terms of our power series representation for 1 minus x. And here what we want is the power series representation for 1 over 1 minus x quantity squared. And we know that this is the derivative of 1 over 1 minus x. And so we can simply differentiate each term of our power series term by term. If we want to do the general series form here, we have the sum from n equals 0 to infinity of x to the n, which would be n times x to the n minus 1. That's our power rule applied to the power function x to the n. And of course, if we did each term individually, we could have the derivative of x being 1, the derivative of x squared being 2x, the derivative of x cubed being 3x squared, and so on. And those would be the first 3 terms of the power series representation for 1 over 1 minus x quantity squared. The second part of our problem asked us to find the exact value of the series n equals 0 to infinity of n over 4 to the n minus 1. Notice that we can rewrite this series in the form n equals 0 to infinity of n times 1/4 to the n minus first power. If we compare this series with the power series representation of the function that we just derived, we notice that what we actually have here is the same series with x equaling 1/4. In particular, this is simply going to be equal to 1 over 1 minus 1/4 quantity squared. Here we're just replacing the x with 1/4 in our series, and therefore the x with 1/4 in our function to obtain 1 over 1 minus 1/4 quantity squared. Going through the arithmetic, we see that this will equal 16/9. And so our series from n equals 0 to infinity of n over 4 to the n minus 1 has a sum of 16/9. Notice that we couldn't previously do this using all of our convergence tests. We could certainly determine that this series converged and using a number of tests, but we were unable to find the exact sum. One benefit of power series is that it does sometimes allow us to find exact sums of series, such as in this particular example. If you'd like to try a similar example, pause the video and find the power series representation for f of x equals 2 over 1 minus x quantity cubed. As a hint, you might consider differentiating the function considered in the previous example. You can resume the video and the full solution will appear in a few seconds. Following the provided hint, if we differentiate the function from the previous example, 1 over 1 minus x quantity squared, we obtain the function considered here, 2 over 1 minus x quantity cubed. This means in order to find the power series representation that we're looking for, we simply need to apply term-by-term differentiation to the power series obtained in the previous example. So we start with the power series representation for 1 over 1 minus x quantity squared, which we saw was the series from n equals 0 to infinity of n times x to the n minus 1. The first few terms of this would be 1 plus 2x plus 3x squared plus 4x cubed, etc. Differentiating each term here of our power series, we obtain the desired power series representation to be the series from n equals 0 to infinity of n times n minus 1 times x to the n minus 2, which has the first several terms of 2 plus 6x plus 12x squared.